Well, good morning. It's Monday, November the 2nd. Okay, beautiful, crisp morning. This is cold. Okay. Let's look at doing these Lewis dot structures, seeing what parts you got right, and I'm going to give you a few little tips as far as just things to know. Okay. So if we look at this first one, SO3. What are the steps to drawing the Lewis dot structure? What's the first thing we need to do? The number of valence electrons. So sulfur and oxygen both in the same family, they each have 6. So 6 plus 18, we have 24 electrons. Okay? Step 2, just connect everything with single bonds. Now, generally speaking, oxygen is not going to bond to itself in a chain. It's always going to build around. Oxygen bonded to oxygen is called a peroxide. It's very unstable. Oxygen's in the -1 oxidation state instead of its normal -2. It doesn't like to do that. Okay? It will under rare occasions, and they're called peroxides, not normal. So in a case like this, we want to build the oxygens around the central atom. And the central atom is always going to be the one you have the least of. And if there's a tie again, it's going to be the one that has the fewest number of valence electrons. So I'm just going to say sulfur, oxygen, 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 all single bonds. Now I go and I have 24 electrons. I start always doing on the peripheral ones, the outermost ones first, filling their octet to 8. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Well, that's all 24 of my electrons. Okay, so I can't add or take away any more electrons. I have to use exactly 24. What's the problem here?
Sulfur only has 6.
Sulfur only has 6. When the central atom is electron deficient, you've used all of them, but there's not 8 on the central atom, that's when you have to do multiple bonds, double or triple bonds. Okay? So I call it the Robin Hood principle. We steal from the rich, share with the poor. Okay? We don't give it all to the poor, we just share some with the poor. Well, this needs 2 more electrons. So I really can pick any one of these, and this is a special case we'll talk about later on this week, but we can pick any one and just take a pair and share it. You could have had the double bond here, you could have had the double bond there, it doesn't matter. It doesn't matter where, you could have the oxygen, oxygen, oxygen down here, none of that matters. You have 3 oxygens around the sulfur, 1 being a double bond, the other 2 being single. Okay, we good with that? What's the second one? HNO2. Okay, so this is another good one. Okay? So we count our electrons. 1 plus 5 is 6, plus 12 is 18 electrons. Okay? 18 electrons. So what's going to be my central atom? Nitrogen. Now, you could put a hydrogen right here, but here's tip number 2. When you have hydrogen and oxygen in the same compound, hydrogen and oxygen will generally go together. They bond. They have a thing for one another. I like to say that hydrogen is oxygen's O, H-O. Okay, they just go together, okay? They just go together. So you're not going to put the hydrogen on the central atom. You're going to put the hydrogen, either oxygen, pick one. It doesn't matter which one. Okay, I see a lot of erasing going on. That's just going to be something, unless they give you a structural formula and actually say that the hydrogen's somewhere else, the hydrogen will be on the oxygen. That's a very stable bond. That's where the hydrogen's going to go first. So, I have 18 electrons, 2, 4, 6. Hydrogen only needs 2, so we don't put any electrons around the hydrogen. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay? Are we done?
No.
Zoe, what's the problem? Zoe, what's the problem?
Not enough electrons in nitrogen.
Not enough electrons on nitrogen. So what do?
Double.
Double bond. Now we steal from the rich. Which one's richer, this oxygen or this oxygen? the top one, right? Because this already has its two bonds formed here. So we're gonna steal from the rich, form a double bond with the oxygen, okay? So it's a puzzle, but there's the steps to doing it. If you follow the steps every time, it works. Okay, what's the next one?
SiO2.
SiO2. Silicon dioxide, also known as sand or quartz crystal. So, silicon has 4, oxygen has 12, so we have 16 electrons. Obviously, the silicon is the central atom, oxygen to oxygen. Now, how you wrote that, if you wrote it bent, that's 100% fine. We're gonna talk about shapes later on this week, and again, we'll have a system on the shapes. So, 16, 2, 4, 6, 8, 10, 12, 14, 16. Silicon's electron deficient, right? It needs 2 more pairs, it needs 4 electrons total. We're not gonna steal both from the same oxygen. We're gonna take 1 from each one, just to kind of make it more balanced. So we're gonna end up with a double bond, 2 double bonds. Is this all making sense?
Yeah.
Okay? So, I'm gonna do, what's number 4?
I3 minus.
I3 minus, so this is another good one. First off, what's the minus mean? Extra electrons, so it's 7 times 3 is 21, plus 1 is 22 electrons. Okay? Now, this one's a little bit easier too, because which one's the central atom? Iodine, one of them. Okay? So it's gonna be I. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. But I need 22. So where do those extra electrons go? On the central atom, and just pick a spot. Now, it's always in pairs. You're never going to go 1 and 1. Electrons are always in pairs. Okay? So, just to make it fit better, I'm going to kind of like move this pair over here and then just do it like that. Now, if I'm doing this Lewis dot structure, I do my 20, I'm right there. The way I'm gonna do that is I'm gonna put 1 there and 1 there, not have to erase, but I don't want you to think that I'm splitting the pairs, okay? They're always in pairs. Okay? What do we call, how many electrons are around this central atom now? 10. So that's called what? An expanded octet. What's the only rule? Which elements cannot form an expanded octet?
First 2 rows.
The first 2 rows, but really, hydrogen only forms 1 bond, we know that, okay? Helium doesn't bond with anything, so it's really just gonna be boron through fluorine. Those are the ones that cannot form an expanded octet. They're too small, that's all you need to say, it's too small to form an expanded octet. No other explanation needed. Okay? Now, when you have an ion also, you put it in brackets and put the charge outside the bracket. That just says that the minus charge is evenly distributed on the whole thing. It's not on any particular iodine. Okay? So, when the central atom is electron deficient, we have multiple bonds. If you have extra electrons, they always go on the central atom. No need, if you have an expanded octet, you won't generally have double or triple bonds. Okay? What's the next one? 5. What is it? Tell me what it is.
CCl2F2.
CCl2F2. Have you ever heard of a chlorofluorocarbon, a CFC, that they're bad for the environment? This is one of the original freons, which is a chlorofluorocarbon, okay? And so most refrigerants are some type of CFC, and they've gone through now and gotten more complicated to where they're a little bit less damaging to the environment, okay? this right here is a very stable molecule. And so when, back in the day, when I had, this is early 80s, I had an old well, I bought it brand new, but it tore up really fast because that was when Chrysler was making junk. But I had a leak in my air conditioner system. So I could go to the auto parts store, buy a can of Freon, and I had a little adapter, and I could put the Freon in myself, okay? And all the Freon would leak into the environment. If I was changing something out, you just let it go off. But it turns out that this would rise up into the upper atmosphere. It's stable, but when it got to the upper atmosphere with the UV radiation, it would cause this molecule to decompose. And you get free floating chlorine atoms. Well, they would go in and react with ozone and destroy the ozone, or react with the ozone and change it into oxygen. Well, what do we know about ozone in the upper atmosphere? What's it do? Blocks UV light, okay? So there was a ozone hole forming over Antarctica to where, and that's where, because of the magnetic poles and all that kind of stuff. But they found that one chlorine atom can destroy up to 20,000 ozone molecules just because of the chain reaction. It just keeps reproducing itself and just messing it up. So they banned this. Now in order to do anything with Freon, you have to catch any of the escaping gases. You have to have a Freon retrieval system, a canister to collect it. And only certified mechanics can actually get the Freon. Because you have to have that equipment, so the DIYer like me can't do it anymore. Anyway, that has nothing to do with the Lewis dot structure, but that's about CFCs. Just that's why chemistry is, the reality of chemistry. That's this is what we're here for. Learn how are we using chemistry in life. So what's my central atom going to be? Carbon. And then we're just going to build around. And it doesn't matter where the chlorines are or where the fluorines are. They can be in any order. You just have 2 and 2 around the carbon. Okay? Order doesn't matter. So I got to count. I have 4 valence electrons. These are both in the same family, so I have plus 28. So I have 32 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 6, 28, 30, 32. We like that? Nice and easy. Everything's got 8. That ain't broke, don't fix it. Are we good? Mm-hmm. Okay, let me just show you the rest of them. Then I'm going to throw you a curveball.
Yeah.
Now, I have all of the information. I have bond angles and shapes on this answer sheet. All you have to worry about right now is the Lewis dot structure. But I don't even really want you to copy the other stuff down because I need you to figure that out later this week. Okay, so we did the SO3, SiO2, I3, so here's your NF3 at the top right. Notice we have 2 expanded octets here and here. Tell me if I need to raise it up. Most of y'all, I'm assuming, have gotten 6, maybe even 7, 8, 9. Notice here carbon is the central atom because it has 4 valence electrons versus nitrogen having 5 valence electrons. That's how you know carbon is going to be the central atom. Okay? You need to share with the nitrogen. Hydrogen can't form a double bond. It's way too small. It has 1 electron. So that it has to do a triple bond with the carbon in order to, the carbon has to do a triple bond with the nitrogen in order to get its 8. Okay? That's about the 8 octet rule. Notice here, krypton. Some noble gases can form compounds with a highly reactive fluorine and maybe oxygen. Okay, but they're few and far between. But if a noble gas is the essential atom, it will always be an expanded octet because you're starting with 8. So as soon as it shares any, it's going to be over 8. And then, what's unique about this one, BF3? Only has to have 6 electrons. Now, which group of elements only form stable molecules with only 6? Group 13. You just have to know that. It's an exception to the octet rule. Okay? It pops up and you just have to know. Okay? So you put a star by it, you just don't make a mental note. Somewhere or other, these all follow a pattern. That's an exception. All right? Does anybody have any questions about any of these? You guys are really looking dead this morning. Okay? It's supposed to be a crisp, cool morning. It's supposed to, perk you up a little bit, I think. No? You guys just are so not used to it. It's taking you a while to get back in shape. It's been since March that you've been having to come 5 days a week, and you're so used to getting up at the crack of noon and doing virtual. Welcome to my world of having to show up to work every day. All right. Now that we understand how to do Lewis dot structures, I got to throw you a little bit of a curveball.
You love a curveball.
So if I'm looking at sulfuric acid, H2SO4, I want to do the Lewis dot structure for this one. I do sulfur, oxygen, 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 oxygen. Hydrogen, again, is going to be on the oxygen. Pick 2, any 2. It doesn't matter what 2 oxygens you pick. You put the hydrogens on. Then we go through and we count. We have 2 plus 6 plus 24 equals 32 electrons. Okay? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Everything's got 8. It looks great. But if I'm going to calculate the oxidation state of sulfur, the quote charge on sulfur, what's the oxidation state of sulfur in this? What's oxidation of hydrogen always? Plus 1. Since we have 2 of them, it's going to be plus 2. What's the oxidation state of oxygen always? Minus 2. We have 4 of them, so the total negative is? Minus 8. Compounds always add up to 0, so sulfur is going to be? Plus 6. Now, what that really means, is this on the screen?
Yes.
Okay? Sulfur has 6 valence electrons. So if I go in and I can put, I'm just going to use X's to do oxygen's electrons. Don't do this on the AP test because an electron's an electron, there's no difference of electrons of each one. They want all dots, but I like to kind of show where the electrons are coming from. Okay, so those are those 2, well, let me be consistent with that drawing over there. Those are those 2 oxygens right there, and hydrogens. Well, how does oxygen bond here when it's already got a lone pair? Well, oxygen has 6 electrons, and they can actually just rearrange and bond like this, to where both electrons of the shared pair come from the sulfur. This is called a coordinate covalent bond. Worth writing down. A coordinate covalent bond. Both electrons of the shared pair come from the same atom. Okay? Both electrons of the shared pair come from the same atom. Now, once formed, and we can refer to this as a CCB, coordinate covalent bond. Once formed, it's identical in strength and characteristics to an ordinary covalent bond where one comes from each one. So when we're drawing our Lewis dot structure, we don't really care the source of the electrons at all. We just do it and count and put them, because a coordinate covalent bond and a normal covalent bond are exactly the same, so there's no real need to differentiate. Okay? So does everybody have that definition? Coordinate covalent bond. Both electrons of the shared pair come from the same atom. But once formed, it's identical. So we really don't even have to worry about this. The only reason I'm showing this is so we can figure out what this +6 really means. And why it's going to lead us into this next step. So, oxidation state is the number of electrons an atom tends to gain or lose in an ionic bond or share in a covalent bond. That's what oxidation state is, the number of electrons it tends to gain, lose, or share. In an ionic bond, however many it tends to lose or gain is going to be the same as its charge. Okay, because they're going to gain and lose the same amount. So oxidation state and charge +1, 1 plus, you know, they're going to be exactly the same. But in covalent compounds, they can share various amounts, especially with oxygen, because oxygen can do this unique coordinate covalent bond. So when we say that a sulfur is in the +6, that means it has all 6 of its valence electrons involved in bonding. What it doesn't mean is that it has a +6 charge on the sulfur. It hasn't lost 6 electrons. It's just got 6 electrons involved in bonding. Okay? I'm just going to give you one more example. Chlorine has 7 valence electrons. It can form the ClO- ion. ClO-. What would be the oxidation state of chlorine in ClO-?
+1,
How did you get that, right?
because net charge is -1 and oxygen is -2.
So this has to be +1. Chlorine wants to be negative, but the less electronegative element is forced to take the positive oxidation state. So in the rare case that chlorine bonds with oxygen or fluorine, chlorine has to be positive. Otherwise, every other element that's more electronegative is always going to be -1. But, so that +1, what does that +1 mean? It means it's got 1 electron involved in bonding. Okay? But it can also form ClO2-. That's the hypochlorite ion. This is the chloride ion. What's the oxidation state of chlorine in this one? +3, right? Because this is -2, -4 has to equal -1. Does everybody see how I'm getting the +3? Anyone question? Speak up, come on, be bold. Okay? So the way we draw it is we just put another oxygen right here, ClO2. So chlorine is now in the +3 because it's got 3 of its electrons involved in bonding. That's what my oxidation state is telling me. So then we can go to chlorate, ClO3-. And what's the oxidation state of chlorine in this one? +5. Because -2 is -6, has to add up to -1. So when we draw it, we just put an oxygen here with another coordinate covalent bond. And then finally, we go to ClO4. So in ClO4-, what's the oxidation state of chlorine? +7. Because all 7 of its valence electrons are now involved in bonding. Okay? So chlorine can be Normally it's -1, but when it combines with oxygen, in this one case, or it combined with fluorine for CLF, chlorine can be +1. In these other three cases, when you got ClO2, ClO3, and ClO4 minus, chlorine can be +1, +3, +5, or +7. So when you go on your periodic table and you look at the possible oxidation states of chlorine, you can see ±1, +3, +5, or +7. It can do that because of the way it bonds with oxygen with these coordinate covalent bonds. Most of the nonmetals are going to have those same types of situations. They're normally got the -2 for sulfur. But it can be +4 or +6 because the oxygens can come in and form these coordinate covalent bonds. It's in the +6 state here. Where am I? +6 state here. If I was H2SO3, H2SO3 is going to look like that. Now only 4 of its electrons are involved in bonding. It's going to be +4. So the oxidation state is telling us the number of electrons that are involved in bonding in a covalent bond. That's why he's put this sign in front, because it's not really a charge. Okay? So, put that last one right there. Now, if I'm just going to draw ClO4 minus, if I'm saying draw the Lewis dot structure for ClO4 minus, I'm just going to say 28 plus 7 is 35, 36 electrons. So I'm going to say oxygen, 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 oxygen. Did I count right? No. 6, 24, it's going to be 32 electrons, sorry. I knew that was wrong. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I don't worry about where the electrons come from. I don't differentiate between a normal covalent bond and a coordinate covalent bond or any of that stuff. I just count my electrons and build it. But the reality is that we're trying to keep track. This is what our oxidation state is telling us, how many of the electrons are actually involved in bonding. Y'all good with that? You're so dead that it's hard for me to tell if you're getting this or if you're just bored silly. Or, I mean, you might be bored silly, but are you still getting it? All right. So, the oxidation state, sulfur +6. That's not a true good indication of the actual charge on the sulfur. So we have a thing called formal charge. Formal charge. Which means that we'll do that when you come back from break. Because some of y'all need to walk around and get some energy.